Yeah, so also from my side again, welcome to all of you. So within the next about 20 minutes, I want to briefly introduce you our basic products that we work on, and especially in this context of the World Bank project that I already briefly mentioned, and where the basic idea is to create, let's say, new advances to understand risk and increase resilience in African cities. And for that purpose, we basically want to use techniques that we already developed in the context of the so-called World Settlement Footprint Suite. What exactly this is, I will show you soon. So basically, the project that we are currently working on is aiming at the satellite monitoring service for urbanization in Africa. And the project started last December, and it will, let's say, end next year in March. Although, let's say, some of the major deliveries are due by end of this month and beginning of the next month. The key objective, as you could see from the title of this project, is understanding risk and increase resilience in African cities. And to do so, the scope, let's say, of this project covers four major topics. First step is to update or provide an updated list of urban centers in Africa with a population of more than 10,000 inhabitants. Then we are supposed to demonstrate monitoring services, so kind of a constant observation capability for urban areas, and with respect to several different parameters. The first one is the build-up extent, so it's simply a build-up mask where we delineate the settlements. In this case, cities more than 10,000 inhabitants, but actually with the technique itself, we can also even detect and map smaller settlements and villages. The second parameter or indicator is the build-up density. So once we have identified build-up areas, we also want to know how dense the build-up area within this. So you can imagine, or yeah, this as a, we call it imperviousness. So it's per pixel, the percent of impervious surface. Impervious is usually roads, build-up area, etc., or everything which is not green. And then a third parameter, if it's about the build-up area itself, is the build-up structure in 3D terms, so the building volume. And that's, of course, what the major topic of today's, let's say, telecon here is, or videocon. Apart from that, we are supposed to model based on our new build-up area data, also the population in combination with population statistics that we have. And then, and that's why it's even a different section, let's say here, shown, we are also supposed to work with temporal data, multi-temporal data. So for instance, urban growth mechanisms. So how did the urban area develop? Was it more, let's say, expansion? Was it infill with the new area that appeared, etc.? We are also supposed to analyze trends, and we want to go for frequent updates of the data, so yearly or even quarterly. So 4 times a year, let's say, for instance, for certain cities, we can come up with a map of the latest developments. Finally, all this is supposed to come together in terms of evaluation and assessment of the hazard risk analysis. So we want to link this data that we generate, so from the spatiotemporal, let's say, characteristics with hazard zones that we also receive from different sources, in order to finally identify where and how many people are under a certain risk. And all this finally is also supposed to be provided in a dashboard, so a web portal, which is open and free and usable for everyone. So we started already some years ago at the German Aerospace Center, DLR, with the mapping of build-up areas. So one of our first large-scale analysis was the global urban footprint, where we started in 2012. It was a global map, first time in the very high resolution of 12 meters. And for that purpose, we fully automatically, let's say, analyzed radar images, about 180,000 with a 3-meter spatial resolution collected by the German radar satellites TerraSX and TandemX. In total, and that's why we usually work very highly automated, we had to manage more than 20 million files. And this was for us kind of a success story, the entire mapping initiative, because so far we have more than 600 international institutions from 44 countries using it. So for all scientific purposes, this is open and free, but there's a little but, let's say, if it's a commercial application, for instance, or a non-profit, but still not scientific, there are little license restrictions. This is actually due to the fact that this mission and data that we used was implemented in a public-private partnership with Airbus, and there's also commercial licensing behind it, and that's why it's not completely open and free. And that's something that we wanted to change, and the data you will soon come in touch with, I assume. So with that, we defined kind of a successor for the world settlement, for the global urban footprint, which is the world settlement footprint. There's a couple of innovations with it. Some are technical. I don't want to go into all the details here, as you can see on top. But one of the most important ones for us is this second point here, the open and free input data. So we go for the European Sentinel 1 and 2, and in an older version, we also went for the Landsat. And all these data sets are open and free, and also with our policy, with the product, we can then distribute it to all interested users. Also, we expanded, let's say, or extended the thematic scope of the product. So it's not just anymore, as it was in the global urban footprint, a binary mask, which just gives you build up, non-build up. But now you see we have this version as well, of course, we call it WSF 2015. So it's an update for the year 2015. But currently, actually, we are also already working on update for 2019. It's a binary version, but then we expand this, and we also on the one hand want to describe the density. So this is imperviousness that I described, and I will just very briefly show you an example of these products soon. We have the population within the build-up area, and we have an evolution which building volume within that cell. So as I said, just for you as a background, the World Settlement Footprint 2015 is a global map here shown for Africa with a 10-meter resolution, which shows you in black in this visualization all build-up areas. So these are settlements. And here I have to mention it's not roads, it's just roads within the settlement, but basically it's supposed to just show you the core area of settlements itself, the settlement body, not infrastructure in terms of railroads or other streets. Then let's say we could also show, and there are publications behind it, that this data set is most accurate at the moment, so more accurate than the existing data sets, for instance, the GUF, the Global Human Settlements Layer, also the Global Land Cover 30. I also can show you now first results already for an even update from the 15 to the 19. This is shown here. So we have this for several cities. For instance, on top it's Accra in Ghana. We have it for Lusaka in Zambia here shown, and or Aba in Nigeria. And then, of course, the nice thing is here shown on the basis of Pretoria in South Africa. If you have the status in 2015 based on the WSF 15, and then in this turquoise color here, we have the latest status in 2019, and then you can easily identify where there's been an urban growth. And that's the basic idea of our techniques. And then, of course, if you go back in time, this we can only do with Landsat. So in a 30-meter resolution, that's the so-called WSF evolution. It's now shown on the basis of Dar es Salaam. So here you can really see literally the city growing. And every black spot means there was in a certain year, let's say, a new establishment of a build-up area. This is, let's say, the colored version of this. So you can see in the color bar, everything that is red was there already in 1985. And then over the different colors, you can see when different other structures appeared in time. And let's say this purple color would, for instance, then represent the latest stage at 2015. And based on this, of course, I showed you at the beginning, we can then start deriving trends. Here it's just the different regions in Africa, so Northern Africa, Southern Africa. You can see the settlement extent in general, how it developed. And there are, as you can also illustrate or see here, sorry, in this illustration, there are significant differences between the different parts in Africa, for instance. But actually, you can break this information down to whatever unit you are interested in. So it can be administrative units of municipalities or even a fixed grid over Africa. Another example here is the cumulative percent growth. So they all start with the area in 1895, and then you can see in their cumulative percentage how they increased. Then we have the same information, not just binary, here shown in this example from Johannesburg, but also in the imperviousness case. So you see in red means it's 100% imperviousness, so fully covered with building or road or some paved area, whereas the green, pure green would mean that it's vegetation within the settlement area. And also there you can see then over time, for instance, how different areas evolve. So others are even densified, so they become more red, let's say in this case. And of course, at the same time, you see, like here on the left-hand side, for instance, when new build-up areas appeared in general. Then I mentioned that we can finally combine this with population data. And here, this is still a bit static, let's say. Two examples from Dar es Salaam again. So that was the, from our case, in our case, modeled population distribution 1988. The basic idea here is that, let's say, the higher the build-up density that we described, the higher is also the allocation of population. And of course, for the larger district of Dar es Salaam in the city, we have the population counts at that time. Then we can simply disaggregate the population. So that was the status in 1988. This is 2012. So you can see there's a tremendous growth and also a different population distribution. But that, let's say, was all for you to give a bit the frame. And one of the more, let's say, or the latest developments actually, and the more complex one or most complex one is the moment the World Settlement Footprint 3D, where you come in and where we are very glad and happy and that you can gladly support us with that initiative, because you might imagine that for us, from the scientific point of view, especially, and also from the product specification point of view, it's very important to get and develop a very thorough understanding of the accuracy of such a product. So what we want to do with that is we want to derive the average building height within 12 meter pixels that we have from height data that comes from the Tandem X model that we have at hand at DLR. And therefore, of course, to really see how good we are, we need accurate ground truth data. So collection on the ground, and that's where we are, as I said, very happy that you can support us. So just for you to give you a brief insight, a bit more detailed now on what this product means. So basically, there are actually a couple of inputs. On the one hand, we have the Tandem X height model, so digital elevation model or surface model that you can see here on the top left. We have a settlement mask, in this case, the World Settlement Footprint 2015. We also use OpenStreetMap data were available, mainly to identify single buildings. Then we have the Tandem X amplitude. So this is radar data, the backscatter. In case that we don't have, let's say, a building mass from the OSM, we derive buildings, or at least try to estimate the location of buildings from this amplitude data. And we have Sentinel-2 multispectral information. Here we mainly use the NDVI information, which gives us an indication where we have to look for buildings and where we have green areas. Because if you think about the 3D structure, if we see in the build-up area a 3D extent, let's say, this can on the one hand be a building, but it could also be a tree. And that's why we also use this information on the NDVI, which is the normalized different vegetation index. And we can use this to mask certain regions. So from the, I don't want to go into all the details, but let's say from the processing, first step is to generate a normalized difference surface model. And this is actually a digital surface model. So this is actually done by estimating the ground surface in such a height model. So where we have the really only ground points, and then all the other parts are excluded, and then we start interpolating. So with this, we have a surface model. That's what you can see here in the center. Oops, sorry. And then from the surface model, we subtract this from the original height model, and whatever remains in this difference image should actually be a real local height. So usually that should just be buildings, trees, etc. So local vertical structures. And we mask this in the next step with a World Settlement Footprint. So we have this information then exclusively for the build-up area. And then in the next step, we can even within the build-up area use OpenStreetMap, for instance, to have information on the buildings. And then we aggregate, let's say, this information together with the height to finally generate a building mask, which has still heights derived from the 12-meter DEM. Here you always have to keep in mind with the 12-meter resolution, it's not really well suited to, or perfectly suited, I would say, to estimate the heights of single houses. But in general, generally you can see, and I will show you soon these examples, that it already gives you a quite nice indication of the, let's say, general height differences within the build-up area. So just to what I showed you in the scheme now as an image, let's say, this is an example from Munich in Germany. So here it's a famous Theresienwiese where the Oktoberfest is actually. And here you see already in the height model, we have the building structures. So usually this kind of linear local high zones. So the brighter the value, the higher is the height. But what you can also see here is topography. For instance, this is a hill. Here, this is also a river, let's say. At that part, it's the Isar River, and we have a steep slope, let's say. We have a higher part of that, and we have a lower part close to the river, and again, a higher bank on the left-hand side. And the idea is now in the first step with this normalized difference, let's say height model, that we exclude the effect of the topography. So we estimate the ground points, generate the terrain model, subtract it from the height model, and we get this NDSM. And that's what you can see here. So that's just showing you now the relative height above the ground. And there, as I said, all the topography, if you still keep in mind this place here where they have the higher bank, and also here, this is removed. And now we just see the local heights, actually buildings, but also trees. Then we aggregate this, and it's a different procedure. I don't want to go into the details here. It also has something to do with the specific German security law. We are not allowed to go for the full resolution in the first step. So we aggregate the heights, the relative heights that we accumulate. In this step, actually, we already do the masking before of the vegetation. So here only, let's say, heights are counted if they really come from a building, or at least where we think it's a building. And then afterwards, we distribute this information again back to the building masks. In Germany, here in Munich, for instance, this example, we had the OSM mask, which was very good. So we have accurate information on the buildings, and then we allocate the average height, let's say, that we estimated. And there you see, for instance, in this case, blue, as you can see on the lower left, means it's almost 0 meters, so low areas. And here, this is, for instance, also the Theresienwiese. I have to say, in this example, for instance, it was even indicated there are buildings, but at that time when we measured, there was nothing, because it's only temporarily. That's why we have a height of 0. Also here, in some official data, that's railway tracks, but there's sometimes it's called, assigned as a build-up structure in this class, and that's why in this example here you see there's a 0 height, and of course we could also use this afterwards to remove it. So that was just a test example, but here you see in the inner city we have higher buildings, and also this let's say yellowish orange colors also give you such an indication. And if we zoom in, what I said earlier, these are really single buildings here. Now, this is a BMW factory, for instance, and you can see that, of course, we don't have a homogeneous height estimation, and it's not really, let's say, sometimes 100% accurate, maybe for the different buildings. But that's exactly what we now have to find out with your, let's say, validation campaign, how good we are really at the building level, and that's why, let's say, we would like to define with you together how one can collect this information in order to help us to understand how accurate we can estimate, even on the building level, this kind of data. And as I said, the idea is then this method works for entire Africa, actually even globally. So then we can have a very good understanding of how accurate we can describe the 3D structure of cities. And just to give you a perspective, what we finally want to do with it. So these are different examples from some cities in Africa where we derived between 2 time stages here, 2000 and 2015, the urban growth. Also in the colors, you see already indication what kind of growth mechanism it was. For instance, blue means it was inclusion or leapfrogging. So it was really outside. Then we have an extension. That's the outside part as well, that it's completely new developed without any context. And the infill is the reddish one, means that it was newly an open space, let's say, within the old settlement core, which has now been developed. And of course, what we want to do, and this is an example, if you combine now with the 3D information, and for instance, even have the evolution where we have different time steps when this area appeared, want to estimate, for instance, what's the average building volume for this for this area, and also for the certain time and or the growth mechanism. And to do so, of course, we first need to have a thorough understanding of how accurate the data is, what the error margins are, and then we can also decide how accurate these kind of analysis are, or in case, what kind of specific improvements we have to do. And that's why, as I said, you come in, and it was kind of a rush through our data sets, and especially the latest 3D data. And of course, I'm happy to hear and discuss with you later what you can do in this context. Thank you.